So, first of all, why are we here? Why do we come to conferences and all that? And really, I think the big thing is to be exposed to new ideas, right? And having joined you over the last 3 days, it's been really wonderful. And I have been exposed to new ideas because I wouldn't have normally come to this conference because I really wasn't even aware of it. And I was invited. So let me just help motivate this about being exposed to new ideas. Anyone read this book, The Black Swan? Yeah, this is a good book. This is Taleb who wrote the book. But he specialized, he was like a Wall Street trader. He specialized in figuring out these, thinking about black swan events, things that would like tank the stock market and such. And what's a black swan event? It's something that's an outlier, that has an extreme impact on the world. But then retrospectively, after it happens, everybody goes, oh yeah, we should have known that was going to happen. But of course, you cannot predict these things. These are unknowns, black swans. And some examples of black swans are 9/11, World War I, the Depression, things that really had a big impact on the world. And you also can have good black swans, like finding penicillin and the existence of human beings. Like, who would have thought before there were human beings that some creature would become super intelligent and then take over and colonize the whole Earth and then kill off most of the other creatures? Like, we didn't expect that, right? So now for thinking about like cloud and like mainframes and things, right? You might worry about black swan events, right? Because they could take out your data center, right? So you want to locate them other places. But what really fascinates me was always thinking about the good black swans. How do you promote good black swans? Because you can't predict where they're going to come from. And basically the advice is meet lots of people, like we're doing here at this conference. Expose yourself to diverse ideas, like at this conference. And take advantage of opportunities. So I was asked to speak here. I took advantage of this opportunity. Because you just don't know who you meet, what neat idea you'll see. And it's also the strategy of venture capitalists, right? They don't know which company is going to take off and be worth $1 billion. So they invest in lots of them with limited downside, hoping one of them has unlimited upside, right? And so in your life, you want to take advantage of very small, little risk things, thinking that one of them, can really pay off. So starting to talk about game AI, you might have seen this. This is very recent. DeepMind created this thing called AlphaStar, and it plays this game called StarCraft 2. But they used a deep neural network trained with supervised learning and reinforcement learning to play this game. And this game is considered harder than Go, right? And recently it did beat some, maybe not the best champions in the world, but very highly rated ones. And this was rough. They trained it on 500,000 human games. They had a population of agents where each agent experienced up to 200 years of playing this game. That's a lot of data. Now, why are they putting machine learning on this video game? Well, it's not to make the video game industry better, right? It's to use video games as a tool to prove out the cool concepts of machine learning. So hopefully they can be applied to things that make money. Because this game is really about playing other humans. You don't need an AI like this for this game. It's not going to really benefit you much. But surprisingly, machine learning doesn't play that big a role in the video game industry for game AI. It's just, and hopefully that's what I'll be explaining. But I will tell you about all the architectures that do. So of course, game industry is business, right? Got to make money. It's an entertainment business, which is maybe different than many of you are familiar with. There's a lot of money. $135 billion in the last year. And this is a performance conference somewhat. Performance is a constant concern in the video game industry, right? From day one. You don't run at 30 frames per second, you can't ship your game. And so everybody's thinking about performance. The artists are thinking about performance. The game designers, everybody's thinking about performance. And at the company where I work full time, I actually work on performance tools to help our developers. Okay, so let's talk about game AI. So game AI is actually a collection of things. Think of it like a giant toolbox full of tools that you might need to apply to different games. So it's not like just neural nets. It's just one thing. It's lots of different things. And like architecture, movement, pathfinding, analysis, sensing, these things. Learning is somewhat used in games, not usually what you call machine learning, more statistical, just simple learning. Content generation is a fascinating one. That's the idea of having computers make the content, make the music, make the story, the writing, make the levels. And there's some success in that. But today I'm going to talk about AI architecture and like how do people make AI for games. So game AI is not trying to just destroy the player. The game AI has to support the story, the challenge of the game, whatever the game designers want the game to be, and overall the experience of playing the game. So actually, I just want to pause for a moment. I'm just curious. How many people play games once a month at least? How many people in here? Okay, so how about once a week? How about once a day? No, once a day is a couple? Okay, just curious. Okay, so game AI, it's in the name, AI, intelligence. Is it really about intelligence? No, it's not really about intelligence. What's about in most games is behavior. Reasonable behavior, interesting behavior, entertaining behavior. A lot of the behavior isn't very intelligent on purpose because the game has to be beatable, right? Number one, the player has to beat the game. You're not trying to and it's easy to beat the player. So that's not really the biggest problem. What you're trying to do is make it look believable, right? Make it look reasonable. But can't machine learning make this behavior? And it can. It can. But you could ask the other question is, well, can machine learning write, direct, and act in a play? Because that's what games are. You're making agents that have to act and deliver their lines and do all these things, and it should be in service of the game, which is an entertainment product. And so asking machine learning to do that, well, that's pretty rough. There's a lot of decisions, and there's a lot of creativity and stuff. So really, the bigger problem is having humans, having the developers or the people be able to direct the game AI, direct the agents, and like how is that done? So in a way, I could argue that the biggest problem for games is or game AI is really getting humans to be able to author behavior. And it's a really tough problem. So this is Kevin Dill. Kevin Dill's been in the game industry a long time. He worked on the original Red Dead Redemption. Red Dead Redemption 2 came out very recently, and I think it may be one of the most expensive video games ever made. I'm trying to remember the numbers, something like $900 million. Very expensive game. So here's what he said. He said, human-authored behavior is the absolute right answer in this domain. In some ways, I think we're not even really in the business of building AI. We're in the business of building domain-specific, highly customizable, carefully constrained programming languages. What we do is we find better ways to enable humans to define how the computer should behave, which is fundamentally what programming is. And we as a community, Game AI specifically, have led the charge in this domain for 2 to 3 decades now, and we've made enormous strides along the way. Hell, the military simulation industry is only now figuring out things we did 10 years ago, like behavior trees, for instance. And he would know because he works at Lockheed Martin for the last 5 years or so, working on simulations to help train soldiers. Just curious, he says, the military industry just discovered behavior trees. Who in here knows what a behavior tree is? Right? You guys haven't discovered behavior trees. Not that you need them, but I will actually cover that because that is one of the most popular architectures now. Okay, what do we want from our game AI architectures? Like a lot of software, we want it to be scalable because we're trying to do bigger and bigger things, and scalability is always an issue. We want the code to be reusable so we can reuse the stuff we wrote in lots of different places. That's always nice. And we got to get quick iteration. We need to constantly try things, test them, try things, test them, try things, test them in the game. And the faster you can get that iteration, the faster you can make your games. And games take years to make. So iteration time is very important. So how do you achieve these things? Well, for Scalable, a lot of times you're looking at hierarchical techniques, and we'll see a couple of those in the architectures. Reusable means modularity of some kind. And quick iteration means that while the game is running, I need to be able to change the code instantly, have it reflected in the game, and test it without rebooting the game, without recompiling the game. And so how do you do that? Right? That's the architecture is also important for that too. So our first architecture kind of is just what we would call scripting languages, also known as DSLs or domain-specific languages. And what's going on here is that we want to, the game is written probably in C or C++, but we need to have a scripting language that's an abstraction. So maybe people who aren't programmers can change the game. Maybe they can write lightweight logic or something. So, or even programmers, by making a higher level language, right? That means faster programming. That means you can work faster. Number two is hot loading, and that is that the game is running, you change code, you change real logic, and you need it to load into the game that moment, do whatever compiling or whatever on the fly to get it inside of the running game, and so that you can test it immediately. And so that's why you would use a scripting language or something. And then number three is no memory management. So C++ requires memory management, but scripting languages generally nowadays don't, and because they have garbage collection and stuff. So years and years and years ago, every game company would make their own scripting language. Oh, it's brutal. It's brutal because people are terrible at writing new languages. And they were only used inside a particular company, and so they're full of bugs and stuff. But they achieved the first two. They made an abstraction, and you could load them while the game was running. In fact, one company even made it so that you could program in C++, and it would compile C++ while the game was running and get it inserted. Recently, games are using now C# and Lua as their scripting languages, which have garbage collection. But the base code is almost always something faster, like C++. Okay, so our first architecture, I'm sure you know, have heard of this. Finite state machines. It's one of the most common software design patterns there is, right? And so for a video game, this is what a finite state machine might look like, is you have the states there in blue, wander, attack, and flee, and then there's reasons why you change between the states. And so kind of the core problem of game AI is what you might call action selection. What action is this agent going to be doing at any particular time? And so if we start in, say, the wander state, they're wandering. And I can always just check what state they're in, and we see what they're doing. And if they see an enemy, they'll go to attack. And then if there's no enemy, they'll go back to wander. Or if they get low health in their attack state, they'll then run away. And then if there's no enemy, they'll go back to wander. Right? Very, very, very simple thing going on here. Now, this worked many, many years ago, like in the 80s and 90s. But then games started getting a little bit more complicated, and state machines do not hold up if you add too many states. And you can kind of do this through a thought experiment, pretty easy. Just say, like, okay, well, what would a state machine look like if it had 30 states? It's not 1,000, it's not 10,000, just 30. Well, the problem with state machines is if you had, say, 30 states, and I wanted to add a state, I have to reconsider all the other states that exist to decide, should I transition into this new state from all those other 30? And then should I transition out of this new state into any of those 30? It's just brittle, right? Humans will make mistakes. It's hard to program, and it's a mess. So you kind of need state machines to stay under 10 states to be reasonable, and you just can't get very complicated behavior if you keep the number of states down. Now, there's a fix. The fix is called hierarchical finite state machines, or HFSMs. And the idea is that you still have like a state machine, but then you put a state machine in a state. And so now you can, actually buys you two things. It makes now a whole state machine can be modular and put into other states. And you can have even another state machine inside those states and another state machine, keep going down. And it's a little bit less brittle because if I add a state to this outside one, I don't have to reconsider all the states that are in the inside one. But still, hierarchical finite state machines are still, unless for the simplest creatures, are still considered, something you probably wouldn't use anymore. Another kind of little design pattern that's interesting for game AI, and it's been around a very long time, is the problem of dealing with interruptions. So you might just have a character that's standing around, and all of a sudden the they decide to build something. So they build like maybe this RTS game, real-time strategy game, and they're building a factory. And you're building a factory, and then someone attacks them. Okay, well now they got to attack back. So now you can have this stack thing and just push an attack behavior kind of on there, and now I'll go attack someone. And then when I'm done attacking them, what I do is I pop it, and I go back to what I was doing before. And so it's kind of this memory of like, so that you can be interrupted and then go back to what you're doing before. It's a very, very simple idea. Interestingly, you can actually add this to state machines. You just have to have an operation inside state machines called pop, so that the state machine can remember which state it came from, and then in attack, you could say pop, and it would go back to whatever state it came from. Most state machines, you wouldn't have an operation like that normally, but you could incorporate that. Okay, well, what happened is state machines, they're not holding up. They're brittle, there's problems. And so around 2004, 2005, games started getting complex enough that these two games both figured out and invented new architectures, or co-opted them from academia in order to make the complexity that they needed. And so the first one is behavior trees, which I alluded to before. This happened in 2004 with a game called Halo 2. And then in 2005, they took academic planning, strips actually it's called, and made it work in these games. These are multi-million-dollar games, and the fact that they were able to ship it and make it work was a testament to like this would actually work. And what had happened is each of these architectures were in these hit games that were the biggest games of those years, and then the people who did it spoke at a conference like this. And when they did that, everyone now knew about it and started using it and started experimenting with these things. So let me talk about behavior trees first. So this is what a behavior tree looks like. You visually program it by dragging and dropping boxes and drawing arrows and all kinds of things. And I'll step through this in a second because this is pretty fascinating stuff. This is like, how do you program visually like this? And this, I don't know for sure. Maybe there's something else, but this might be the most widely used visual programming language there is, because this is in a game engine called Unreal, the Unreal Engine, and there's another game engine called Unity that thousands and thousands of games use, and they both support behavior trees and dragging and dropping and doing this kind of thing. And you can see how you want maybe non-programmers to program, right? But without shooting themselves in the foot, right? Without making the game crash, hopefully, and all that stuff. So this is inside Unreal that I'm showing you right here. And you might know the company just because they have a very popular game out right now called Fortnite. Has anyone heard of Fortnite? Yeah, so Fortnite, this is that same company. Okay, so let's walk down how behavior trees work, because it's really fascinating. And it's really hard to kind of program, get your head around it at first. So our first, we have these nodes, right? And these nodes are trying to decide which of their children should they run. So let's look at the left one. It's called a selector node. And the way a selector works is that it first starts, it's a priority list, its children are a priority list of actions to try. Okay, so the selector will first go down to action 1 and say, will you work? And there's 3 possible responses. One is fail, no, I won't work. Or one is success, I did it. I work. Or the third one is working. Like, yeah, leave me alone, I'm still working on the problem. But what happens is if it goes down to action 1 and it says fail, it then goes back up to the selector and then tries action 2. And then if that fails, it goes to action 3. And if that fails, then the selector itself passes failure back up in the tree. Now, if one of those succeeds, say if I go to action 1, it fails, but I go to action 2 and it succeeds, then we're done. We just go up to the selector and return success upward in the tree. So it's a priority list of things to try, is what it is. And those leaves can be whole trees, right? So, and then it passes this stuff up through it. Now, a sequence node can be thought of as a plan. I want to do action 1, then I want to do action 2, then I want to do action 3. It's a fixed plan that the programmer decides when they program the game. And so the sequencer node will go down to action 1, and action 1 will say success. And if that happens, it goes to action 2. If action 2 says success, it goes to action 3. If that gets success, then it goes success upward. But if any of those fail, it's going to fail. The plan failed. If we get to action 2 and it fails, we just fail. We don't try action 3. We fail and go fail upward. It's a very, very peculiar way to program logic. And there's a third one called parallel. And this just means I want to run all my children at the same time. Maybe I'm waiting for success from all of them, or if any of them fail, I'm going to fail, is kind of how that works. Okay, so back to this behavior tree that's inside this Unreal Engine. So just to kind of, now you know enough to kind of see some things. So that top one is a selector. So what it means is that that's priority 1, try that branch. If that fails, then try that one, priority 2. If that fails, try priority 3. If that fails, then try priority 4. Okay? And then we also saw the, I'm going to introduce a new concept I haven't talked about yet. It's called a decorator. And what a decorator is all these blue ones that are kind of at the top of these boxes, and those are just like little checks. And it says, is target set? And if that's not true, then it fails immediately. And so that you can write these little decorator checks, and they just get stored at the top of those nodes there. And then I did talk about the sequence node already, but there's an example of it. And remember, the way it works is that's a plan. Do number 1 first. If that one succeeds, then do number 2. If that succeeds, do number 3. Okay, so it's weird. This is programming as a tree. But you saw from the state machine that programming these agents really needs to be a cycle. It really needs cyclic behavior. So where's the cycles? Well, what happens is that once you would succeed with, say, number 3 there, you would put success, success, and you'd be back up at the root. You're done. Well, you re-enter again and go and try again, and then start at the selector again. And so it is cyclic like that. The leaves, all these leaves at the bottom, those are all the actions. That's the actions. That's what the agent is actually going to do. And so all the internal nodes are just decision nodes to try to get they're called control flow nodes, that try to figure out eventually which thing you're really going to do, what the agent's going to do in the world. One last thing is there's this service node, and this is like a polling kind of thing, where you can set up a poll. So if you're anywhere in the underneath of this, you can set this poll to be like every 0.5 seconds or 1 second or whatever you want, and it will check something, and that's called an aggro check. That one's just named aggro check, and aggro means someone's attacking you, basically. And so it's checking, is there an enemy nearby? Is there an enemy nearby? And if it does see an enemy nearby, it doesn't matter where in the leaves it is, or it's going to steal the control and start it again from that root. So that's another place where there's cycles, and it's not obvious from the picture. And this is actually a problem with behavior trees, right? You can't really see the cyclic nature in them, which makes it a little harder to understand. And when you make a programming language, you want it easy to understand. A blackboard is another weird concept. So this is behavior trees have this idea of a blackboard where it's a shared communication space for all the nodes. So a given node can write down little notes on their blackboard or on the blackboard of the tree. And then later in a different node, it can read that value. And so it's a way to communicate information from different parts of the tree. And so like some of these things set a target, well, they're writing it to the blackboard. Some of these things are checking for the target, they're reading from the blackboard. And the blackboard's usually just implemented as like a dictionary. Okay, yeah, so we already talked about, where's the cycles. The other thing I wanted to say is interruptions. Remember I just showed you that stack, that action stack that was able to deal with interruptions. This thing can't deal with interruptions. It gets pulled out of something, it just has to reevaluate from the root and hopefully get to the same place if you wanted to resume what it was doing. And that's a flaw in this programming language. This is the most widely used architecture for game AI right now. Do we believe it's the final one? No. Right? It's got some problems, and it's got some scale problems. So this all looks great and pretty, but I did hear from someone who works on like the Batman games, I believe it was the Batman games, is that they're using behavior trees, and they have behavior trees that have 40,000 nodes. What? How do you deal with something like that, right? So this, even though this has great qualities of modularity, hierarchicalness, and stuff like that, you get too big and it's still a mess. And the person who got hired, their first job was to look at several hundred nodes of this thing that they had, and it took them several weeks. So you can imagine the problems. So the way to think of a behavior tree is as a static plan, right? It's a plan the programmer decided that this is what the behavior of the agent should do, and they should do these things in this priority and do these sequences of things, and that's the plan of the agent. So this is one way to author. You could actually author this in a finite state machine too, right? It's just the idea is that this should be easier. Now, something amazing, kind of a little weird factoid, is you can convert this logic into a finite state machine. You cannot convert every finite state machine into this. So a finite state machine is actually slightly more powerful, but in practice, because of all the interconnects, it's too hard to use. It's too hard to program. There is some deceptiveness here. I mean, just because like this branch over here depends on the previous branches, right? So to understand this tree is to understand the sequence, the priority of things, and so it isn't quite as modular as it might first look. Yeah, so it's got these properties: hierarchical, modular, and you could say designer friendly, right? This is meant for maybe game designers with no programming training to be able to use. The other thing that happened around 2005 was that other game decided to solve the same problem. State machines are crap. How are we going to solve it? They went to academia and looked at STRIPS, which stands for Stanford Research Institute Problem Solver. And how the planning works is it's kind of really neat. You just give the agent goals, like don't die, defend this spot, patrol this area. And then what happens is there's all these actions that the agent could do, and it's up to a search algorithm to find the most efficient sequence of actions to accomplish the goal. So this is kind of called a declarative architecture because, well, the other one was like with state machines and behavior trees. If you didn't think of everything, it didn't work if it met a new situation. This one's a little more robust. This one just tries not to die and will somehow mix and match all its actions at runtime, evaluating it to try not to die. So it's kind of a neat way. It's got its own problems of debugging and such, but kind of a neat way to go. So how the actually algorithm works is you figure out what the desired state of the world is. How do I want the world to be in the future? Maybe the enemy is dead. And then how is the current state of the world today? Well, the enemy is alive. And then you want to do a search to figure out kind of from my desired state to my current state, which actions will get me there. So shoot. So every action has two things, a precondition and an effect. So shoot has the effect of making the enemy dead, which is what we wanted. But it has a precondition that the weapon is loaded. And so maybe we have to then find an action to load the weapon, but then I have to precondition that the weapon is at hand, and draw a weapon does that, and it has a precondition I have a weapon, but in the current state of the world I do have a weapon, so then there's my plan. But you can see there's lots of other inefficient plans, like I could do the action go to sleep in the middle of this, but that's not a very good plan, right? So we kind of want the most efficient plan. And so one of the problems with this is, one problem is the search takes time, right? So it's not a very efficient algorithm, especially if you have a lot of actions and a lot of state. You have to hold the state of the world in some data structure, and then that's what you're searching against. So it's a little rough. So remember, it was this game that did this in 2005, and it spurred lots of people to try planning. And this company is called Monolith. They're locally here in Seattle. They're owned by Warner Brothers. And they were using this planning system in their games, and lots of games, all the way up to 2014 with this game called Shadow of Mordor. Then after that, they decided, 10 years of this, we need to go to behavior trees. And they ripped it all out. And their latest game, Shadow of War, uses behavior trees exclusively. Now, this is not to say that planning is a disaster and shouldn't be used in games. It is used in games like Assassin's Creed and some, but in limited uses, like The Sims also. But as a core architecture, probably not the right thing. And one of the reasons why wasn't the right thing is these plans tended not to be very long, and it was just much simpler to author the behavior using behavior trees. Okay, another really neat thing is two architectures I want to talk about are utility and smart objects. And these both came about from the game The Sims. Anyone ever play any of the Sims games? Okay. So this is a virtual dollhouse. This game took like 5 years to develop. That's a picture of Will Wright, who was the lead game designer. And you control this family of Sims, and you make a house for them, you buy furniture for it, and they react. And, well, utility. Let's first talk about utility. Utility, this is kind of an idea from economics. Is like, well, if I want to do action selection, if I want to choose which action I should do, one thing I could do is I could score them. I could say, what is the utility of doing each action? So I could score them, something like this, and make it normalized. And so, yeah, it's 60% good idea to attack, 30% to reload, 10% flee. So I could just choose the highest one. A little problem with choosing the highest one, though, is your AI might become predictable. So one thing you could do is use what's called a weighted average, or a weighted random, sorry. And a weighted random is just, I'm going to roll a die using those as my percentages. And so 60% of the time, I'll choose attack. 30% of the time, I'll choose reload. 10% I'll choose flee. This is utility is pretty neat. Let me continue to talk about it. One thing you can also do is you can take the values that go into making these scores. You can make any equation you want to make the scores. But as a last step, what is a very powerful thing to do is to be able to take whatever numbers you get and put them against what you might call a response curve, so that and let's use a concrete example. So ammo. I have a gun. It can hold 100 bullets. Okay. Well, if I have 100 bullets in my gun, do I want to reload? No, I want a 0 reload, right? So if I have 100 bullets, the score is 0. Now, if I have 80 bullets, that's still a lot of bullets. Do I want to reload? Probably not, right? So 80, still the score is 0. But then you can see with the curve, once I get down to 10 bullets, I'm like 100% I want to reload. Now, what's really neat about this response curve is anybody can draw it. Right? Your game designer can draw it, or anyone to tune the system. Another thing is that notice that this curve can be a personality. Like if I'm very timid, scared, right? I might have my curve might be I shoot 20 bullets and damn it, I'm going to reload. Right? And so I have a different personality completely just by drawing a line different. Or if I'm very gutsy, right, I'll shoot all my bullets and then only when I have like 2 left or 0 left will I reload. So it's kind of a neat thing you can do. Oop. And then also another thing is called expected utility, is you can multiply these numbers by a probability. Like what's the probability of it happening? And that can go into the score. So this is probably arguably more powerful than behavior trees for action selection and finite state machines, because you really have a lot of, it's not just a fixed priority of things to try, it can vary. So maybe these are things we might consider doing: run away, reload, punch, shoot, patrol. And what you do is you have math that goes into coming up with numbers at the bottom of each of these graphs, and then it looks up and says, what should I want to do? And the one that's the highest is reload, because the ammo is kind of low. And you have to redraw these response curves to kind of tune it. But you can see, like with the health one on the left, when your health gets very low, you are going to run away instead of doing any of these other things. It's going to become the highest insistence thing. Although if you use a weighted random, you might not choose to do that, right? Because there is some value in not being completely predictable. So this is very neat. The Sims used utility, but then they used it in combination with this other architecture called smart objects. And to explain this, we start with the game. But if you would remember back to the year 2000, this game had a weird thing where like all these expansion packs came out for it, like that added furniture and things for the Sims to do. So, but now the architectural problem is, how do you make an AI that knows how to use thousands of objects and knows how to use objects it's never seen before when they're just invented and plopped into the game? How do you do that? And in order to pull that off, let me first explain this concept called affordance. So you might have read this book. This is a good book by Don Norman, The Design of Everyday Things. And he didn't invent the word affordance, but he popularized it in this book. And I think this book was from the late 70s, early 80s. I just went to a conference here in Seattle 2 weeks ago where he gave a talk. He's 83 years old right now. It's at the University of San Diego, if I remember right. But anyways, this concept of affordance. What's an affordance? An affordance is the object itself tells you how to use it. And the best example is a door handle. Right? Like that door handle on the right tells you how to use it. It's the knowledge of how to use it is in the object, not in necessarily the brain of the person. Right? It's got this thing. It's perfectly made for you to grasp. You grasp it, you pull. Right? Whereas on the other side, right, there's nothing to grasp. You have no choice but to push the door. Right? So the object's telling you how to use it. The intelligence is in the object. Now, don't you hate it when you go to a mall or something and there's some handle and you try pulling and it doesn't pull, right? You got to push the door because the damn object's lying to you, right? And that happens way too much for my taste. Okay, so this is weird. Don't put the knowledge of how to use objects in the agent, put them in the objects. So what we have with smart objects is we have a refrigerator, and the refrigerator knows it has food. And it broadcasts to the world, I have food, I have food, I have food. And if there's a sim around and they're hungry, right, they go, oh, right? And then they'll just start walking towards the refrigerator and they'll get the food out and the food yells, I gotta be cooked, I gotta be cooked. Now, going back to the refrigerator, there's one more extra step. The refrigerator, when they drop it into the game, also has the animations that the person has to play to open the refrigerator. So it's all bundled into the object. Like, why would I use the object? What does it broadcast? If I use the object, what benefit does it instill? And what are the animations to interact with it? And because of this, you can mail completely new objects, like a pinball machine, and just drop it in the game, and the character will walk up to it, start playing it. And when they're done, they're rewarded with fun, is actually what they get rewarded with. Okay, so the food goes, I need to be cooked. And the microwave is yelling, I cook things, I cook things. And so you go to you go, oh, okay. And the sim just doesn't know any of this stuff, right? Just goes to it. The microwave gives it the animations to open up the microwave, put the food in, tells it to wait, take it out, and then you have the cooked food and you can eat it. So this is actually, so in the game, what would happen is that you'd have a sim and they'd have these utility scores of all the problems in their life, right? They're hungry, comfort, hygiene, bladder. The room one is a really funny one. The room is, how nice is the room I'm in? And if the room is really like there's garbage and there's flies, which would happen in the game if you left garbage out, and it was crappy furniture, right? Your room score would be low and your sim would be a little depressed about it. And so you'd need to buy better furniture and clean up the place. But here, our biggest problem is that our bladder. Oh my God, our bladder is going, oh, I need to solve this problem. And the toilet's yelling, urinate in me! Urinate in me! And so the sim is like, I guess, right? And it just goes over to the toilet, probably has to go twice, according to these numbers. If the toilet gets clogged, you'll have to unclog it or else it really hurts the room score, right? You don't want to be in a room with a clogged toilet. That's no good. So this is how you combine this utility with smart objects. Now, utility is a really powerful concept. You can go back to the behavior tree and you can make some of those nodes that choose which children to do and score the children, right? Why not? Behavior tree is kind of thought of as a meta-architecture, where you can put any little thing into it. Like, if I want to make a leaf of a behavior tree, a state machine, I can do that, right? Why not? It's just programming. If I want to make a leaf or anything of a middle control node of a behavior tree into a real runtime dynamic planning, I can do that. So the behavior tree is kind of powerful as a meta-architecture because it really opens up neat things. And you could even like have a state machine where each state inside of it has behavior trees. Why not? Okay, so here's a little diagram that they had at the time of kind of conceptualizing this thing. So the sim in the middle is super hungry, a little bit lonely, a little bit bored. So you can kind of picture the refrigerator is pulling the sim, going, I've solved your hunger problems, right? And then the sim is just pulled towards it. So this is just conceptually, right? You didn't see these mountains in the game. But so you go over there and you eat, and you're not hungry anymore, right? Now you're just lonely. So lonely, got to talk to somebody. Oh, there's somebody to talk to, and you just get pulled towards them. Great, now I'm not lonely anymore. Now I'm just bored. And we've got a pinball machine and a chessboard. And you can see it says playful and serious. Well, see, the Sims had different personalities. So if this Sim is like a slider bar between like playful to serious and all kinds of different ones. And so if this Sim was more playful, they'd be pulled more toward the pinball machine than the chess. Because the pinball machine would actually give them more fun points than the chessboard. Also, you had like your need for sociability. Maybe you're a loner, in which case you wouldn't need to talk to people very much. Or you're very social, and so you do need to talk to people very much. And so this utility kind of took care of all these needs, and then the environment is just filled with objects to satisfy these needs. Now, there's no planning happening here, right? It's not doing sequences of actions. It's just being pulled from one thing to another. So I covered these architectures. Scripting languages, hierarchical finite state machines, behavior trees, planning, utility, smart objects. So if I was going to just say like the two things that are used the most in the game industry right now for game AI, it would be behavior trees and probably then utility. But you can see the problem, right? You need to author the behavior like humans need to, just like humans author books, right? You want to make an entertainment product, and it needs to do fancy stuff. And one problem with, say, neural nets is neural nets are great, but then they're only for like one decision. And in games, these agents have thousands of decisions to make. And you're going to need training data. And you can't do deep learning with very little training data. You need, someone once, I remember saying, you're not talking deep learning unless you're talking millions of pieces of data, right? And you just won't have access to that. And as a game is made, it's constantly changing. Right? Day to day, the game is changing. You can't just get training data. It'll be obsolete in 2 days. And you'll have to ship the product. So real problems with machine learning trying to get behavior. Now, machine learning can be used for like detecting cheaters on the internet or something like that. And actually, something that looks very promising is using machine learning to make the animations. Animations are very rough. Ooh. Brutal problem in games. You probably have no idea, but when I worked on a baseball game in 1998, we had 500 animations for a 3D baseball game. Nowadays, like say FIFA, which is a soccer game, will have 8,000 animations for just soccer players, right? And at any moment, it's blending like 20 different animations at once. It's a horrendous scale and problem. Authoring problem, and it's one that the machine learning is already looking like it can help with. Good. So, promoting good black swans. So, right, meet lots of people, expose yourself to diverse ideas. Hopefully I did that today, right? I told you about things you had no idea. No idea this stuff was happening, because why would you, right? Why would you don't go to game developer conferences, you don't do that stuff. But I think, right, it's really important to expose yourself to new ideas and stuff, because you just don't know where that next idea will come. I do want to, I think I have enough time to close with one more thought. Software is a mess. Humans make fragile things like software, right? Software is brutally fragile. It's always breaking. And fragile things, the problem with fragile things, like, say, software, is they don't like volatility. The moment we start like throwing them things that they've never seen before, they break, right? Just like a glass, it just throw it around, it just breaks. So fragile things want predictability, but the real world is not like that, because humans are unpredictable, especially with video games. They're pounding on the video games, but just in the real world, the way the behavior is. Okay, so the world is unpredictable as well. So this fragile stuff is a real problem. But what is the opposite of fragile? Right? So like if you think of a glass in a box, right, that's fragile. What would be the opposite of that? You might say robust. Right? Okay, well, it won't break. But an interesting way to think about it is the true opposite of fragile would be that the glass, every time the package was thrown, the glass got stronger. Right? Doesn't that blow your mind? Like, that's not true of most materials that we make, right? It's just that does not happen. But as a follow-up to Black Swan, the same author wrote a book called wrote a book called Antifragile, and he invented the word to mean the opposite of fragile. And he's like, this is what we want. We want things that are anti-fragile. We want things that get stronger when they're exposed to volatility, when they're exposed to things they've never seen before. So during development with software, we are anti-fragile. The moment it breaks, someone fixes it, right? It's a bug. We fix it. We haven't shipped the product yet. We fix it. Problem is, once you've shipped, right, then it's fragile as all heck, and you've got to update because what else are you going to do? But that's a mess. So why is being anti-fragile so difficult to program? Well, it's because of the darn black swans. You can't predict all the nutso things that are going to happen to your software. And so how do you protect against that? That's like, can you protect against that? Well, that whole book, Antifragile, is kind of to address that there are things you can do to protect against black swans. So in business, actually, one way to protect against black swans is to have redundancy. And you would know this because of data centers, right? You have redundant data centers, right? But the problem with redundancy is it's the opposite of what every business wants, which is efficiency. Right? Every business wants efficiency, right? They don't want to waste money on extra places that have inventory or factories or whatever. They don't want to have two factories that make the same thing, right? But if you want to be robust to tsunamis or something, right, you would need to source parts from more than one place, right? Okay, so how do you survive randomness? How do you survive volatility? What's the answer to this? How do you survive black swans? Well, so the anti-fragile, okay, but how do I get this property? What is it to be anti-fragile? So muscles are anti-fragile. There are things in real life that are anti-fragile. You use weights and tear your muscles, and they get stronger, right? They're exposed to volatility, exposed to randomness, and they get stronger. Humans are anti-fragile. And so what we're really seeing is like life is anti-fragile, right? But it's hard to make life. It's hard to do it. So in the video game world, fragile would mean what we call these procedural architectures like behavior trees or state machines, very fragile, brutally fragile. Robust would be declarative architectures, sort of maybe like planning that I told you about. A little bit more robust. Maybe if you didn't think of the certain situation, it still deals with it. But what you want is you want to be anti-fragile. The only way you're going to get there is to learn. You need adaptive architectures. And I didn't talk about it, but player modeling is something done in the games. It's mostly statistics. You watch statistically you model how the player plays the game statistically, and then you change how the game AI works based on those statistics. And so it's not direct learning. It's not direct adaptation like neural nets. But direct adaptation like neural nets is dangerous to ship, right? Because it could learn the wrong thing. It does not very reliable, maybe. It's impossible to test. It's got some real issues. But right, anti-fragile is kind of where it's at. And so NASA figured this out. This used to be their thing, that they would design systems according to specified performance requirements. And I've heard that many times at this conference. We need to specify our performance requirements. Like, no one's doing this, we should make them do that. But NASA decided, no. We need systems that evolve. We need systems that adapt. We need systems that optimize in real time to adapt to things and functionality and performance to meet the unknown for whatever crap thing happens to us, right? Because when they send a probe out to Pluto or whatever, right, can't fix it. It better fix itself, right? And they have billions of dollars at stake, so right, they're sufficiently motivated to do this. Right? So that's interesting. And so they've done things like this morphine wing, learn to fly, autonomy, swarming, system health management, self-healing materials. Great. So I think here is a neat quote from the book. If you're anti-fragile, it means you're alive. Because that's what it's going to take, right? To get this quality. Now, maybe you're not willing to spend the money to get this quality, or it's just not important enough to you. But right, this is kind of the end goal, though, is to be anti-fragile. And so what would my advice be? Well, okay, let's try to avoid being fragile. We recognize there's lots of these architectures. They're quite fragile. We probably end up delivering robustness, which is the reasonable thing to do. And the best I can tell you is you want, at this day and age, to aspire to be anti-fragile, right? It's an aspiration. We don't know completely how to do it. We're still figuring it out. But it's our hope, because if you have that, you're robust to any black swans that might hit you. So that's all I have. So thank you. I don't know how much time we have, because I forgot to set up my timer. 5 minutes? Wow. OK, I did it. Any questions? I can tell you anything about the game industry.
Has anyone done any benchmarking to compare the particular the behavioral tree versus the planning versus the other to see which one performs the best? And also, are there any constraints on the depth of the behavior tree? Because I would have thought that would affect the performance of the game quite a lot, quite apart from the space considerations.
Right. So I mentioned planning is bad. Planning is very computationally intensive. It's a search.
Okay.
And then rule-based systems tend to be bad. I didn't talk about rule-based systems, but you might need a lot of rules to pull off behavior. Like 20 years ago, academics took a military rule-based engine called SOAR and tried to make it play a video game, Quake 2 at the time. It took them 800 rules to do it. And so it turned out to be very slow to evaluate all those rules. But behavior trees, so you have to understand that like in these games, there's just not that many characters. So running these behavior trees or state machines or things like that, or utility, it just doesn't even show up, really. There are two things for game AI that are the most expensive to do, and I didn't even talk about them. Number one is pathfinding. What that is trying to find a path to some location in the world. It's a search. It's very, very costly. It's one of the most expensive things you can do in game AI. The second thing is raycasting, to know whether you can see someone else. Because to do that, you have to shoot a ray through the world and see if it hits the person first or a wall. And there's a lot of walls in games. There's a lot of polygons. There's what we call bags of polygons. And there's really, it's horribly inefficient to see if the ray will hit a person or a wall. I mean, you can do spatial partitioning and things like that, of course, speed it up, but it's just an extremely costly operation. So if those are the two things performance-wise that kill games. Now, there's some games like RTSs where there's like 5,000 characters. Well, when there's 5,000 characters, anything you do is too much, right? There's almost nothing. You got to make the AI as simple as possible. And to tell you more about this, game consoles have between 4 and 8 cores. AI is allowed to run on maybe 1 core. AI doesn't get to run on all the cores. You get 1 core just because there's things that cost more than game AI. Physics, maybe animation, graphics, obviously, is the thing that costs a lot. So AI for performance, not as big a problem is this problem of authoring it and iteration speed. That's the problem. That's the real crux of it. Now games have horrible performance problems, but for that you want to attack graphics and physics. And after all, AI also is a bunch of if statements when it comes down to it. And so you need a general purpose CPU. You don't want a GPU. And the AI is never allowed to run on the GPU, so don't get any ideas about that. Almost all games are what you call GPU limited, which means they run as fast as they can, and they can run no faster because of the graphics is the limiting factor. And that's just true on most of the consoles and even PC. CPUs is important. You can use up too much CPU overall, but usually it's the graphics that kills you. Any other questions? Yeah.
MilSim was lagging game tech at some point, like it may continue to do so in places. So since you said that, I'd like to know if you are aware of a company called Bohemia Interactive in the ARMA series.
Yeah, I think I have, yeah.
Now, the Marine Corps bought a license.
Yeah, they would know what they're doing.
Like 15 years ago.
Yeah.
And started using it to train combined arms teams. And I have friends that were in units that specialized in like developing the scenarios and rolling it out and training troops on it. And it was pretty cool because it was 15 years ago and they went out and bought this game basically and then turned it into a sim engine for combined arms.
Yeah, it's cheaper to train people on video games. And plus, if you make it fun, people will train more, which is a nice side effect.
That game is not fun to play.
Oh, is it not? Okay.
It's a sim. It's not a game.
But ever since these game engines started incorporating these things, the behavior tree is kind of this de facto standard at this point because the tooling is so good. And so how about this for performance? These game engines are willing to give up 20, 30% of their performance if you can iterate faster and make the game faster and get it out to market. So that is a conscious decision they're making, and they know they could be faster, but it isn't worth making the development time longer. Is it?
Have you ever considered the question or the problem or the notion that we are willing and able and in fact required to spend that much more resource on rendering, pathfinding, raycasting than we do on logic, even when we're trying to train people?
Getting the behavior right is the hard part. It's not the. Are you talking about performance again, or?
Well, I'm talking about the amount of resource that's required to make these things happen.
You mean human resources?
Well, both human and computational resource.
Right. Well, AI is this kind of mushy thing, right? It's easy to stand up something kind of that works, and there's just all these corner cases that break. And so it's kind of like performance requirements where it's hard to make AI requirements. And it's really hard to scope out how long something's going to take, if not near impossible. Because it's not until you actually do it that you realize maybe all the holes that are in it. So, but if the game isn't rendering at 30 frames per second, you're just not shipping, right? And that's going to cost you a lot of money. If you miss Christmas, right, that's very bad. So you can live with subpar AI. You can't really live with subpar like graphics performance. And many games do. It's a matter of time, right? You might put more time to it, it's better. And it just keeps getting better the more time you give to it. And so it's just where are you willing to cut it off and not spend it any more money? And every game is going to be different, right? They're going to have to come up with their own judgment. Is the game about the AI or is the game about something else, right? And so if it's about the AI, well, then they'll put the investment in. Yeah. Any other questions?
Right. Awesome talk. We expected the best and we got better. So, I mean, as somebody who tries to dabble with AI and things, I get asked and ask myself, is there like a no AI solution to this AI problem? So I'm curious, of the body of games that's out there, like does 3% have AI? Does 93% have AI? And also, what are like the non-AI ways of solving the AI problems you were talking about?
Okay, so what percentage of games even have AI, right? So, I mean, it's just so diverse AI, right? Does a word game have AI? Well, it's got to know the solutions maybe to the puzzles, so it has like really lame searching in it, right? Whereas, you know, the bigger the game, right? It's got more AI. So, but then some games are just all about playing other humans, right? And so maybe there's no AI. Or the AIs in things that kind of you wouldn't even think about, like the ambient wildlife, or maybe the level generation, right? It makes random levels that are just trying to make them interesting to play, and so that AI is in that, right? So it can be all over the place. And then you ask, like, is there AI? Can you get AI to solve the AI problem?
I'm saying, games that don't have AI, like how do they do it?
Well, it's humans. Right? If the game doesn't have AI, it's probably because it's just about humans playing other humans. And I mean, with AI, it's so funny. It's like you can, if you want to imagine what the best AI or like a good human level AI is, just imagine paying an actor to do work. Now, you can just hire people to do things. Like what kind of game could we make if we just hired everybody to be the extras inside the game? Kind of like Westworld almost, right? And then you can kind of imagine what is that like? Would we want that? Is that a good thing? Would that sell more games or not? And there is something people love about beating other humans. And once they find out it's an AI, they don't like it. Right? So there's something, it doesn't matter if the AI is identical in behavior to a human. If you know it's not a human, it's ruined. Right? People pay money for microtransactions to beat other humans. Right? To up their little things so that they can feel smug and that they were better than somebody else. But you just don't get that satisfaction from beating AIs. Now, maybe if you made it so realistic that the AI would communicate with you in natural language, and it would you might be able to fool the person, and they'll lapse and then get some enjoyment out of beating the AI. Maybe that would be the case. But other questions? Okay, I guess we're probably at the end then. Thank you.